Welcome to the course on advanced machining process. Today we are going to discuss on abrasive flow machining process. So this abrasive flow machining process is one of the fine super finishing process. Okay. So this is the outline of my presentation. So this first I shall discuss about that introduction to the abrasive flow machining process, then working principle of abrasive flow machining process, then what are the different elements of abrasive flow machining experimental setup, and then parametric analysis for controlling or for achieving better surface finish, and then enhancing the performance of the process. So this abrasive flow finishing process can be modified further for getting higher performance in terms of surface roughness, material human rate. And then we shall discuss about the process capabilities, okay, and then we shall discuss about the application of this abrasive flow finishing process. So first thing comes, why this abrasive flow finishing process comes, why this super finishing processes comes. This super finishing processes is required in nowadays because nowadays this surface finish requirement is in the range of nanometer. So sometimes we need angstrom level surface roughnesses. Suppose we need the missile, in that missile the whatever lenses are used, in that lenses we need surface roughness in the range of nanometer or further in the range of angstrom level. Also the gyros used in aerospace, gyros is used in aerospace applications. There also surface finish requirement is in the range of nanometer range. Also there subsurface damages should not be there and it should be uniform throughout the workpiece surface. Also there are other things are there, like nowadays most of the workpieces are very complicated. Okay. So these complicated surfaces are very difficult to polish by conventional polishing process. Also inaccessible areas are there. So these inaccessible areas have to be, inaccessible areas in the workpiece have to be polished by this process for any finishing process. Okay. And also nowadays these workpiece material are very harder. So we know that harder material, polishing of harder material, we need the tool should be harder than the workpiece material. So when your workpiece is high strength temperature resistant material, in that case you have to go for non-conventional polishing process for polishing all these workpieces. So in all these non-conventional polishing process, loose abrasive particles are used, while in conventional polishing process mostly like in grinding operation, their abrasive particles in their bonded form are used. And in this bonded form in grinding operation, these abrasive particles has a fixed path and it removes materials any complicated surface is very difficult to polish by this grinding operation. So that's why people go for this non-conventional polishing process. So this AFM, why you are going for AFM process? Because nowadays this surface finish, it consists of 15%, it cost of this polishing of any component consists of 15% of total manufacturing cost. So it is very high, this polishing is very high. So cost of surface finish sharply increases when surface roughness less than 1 micron. So when surface roughness is less than 1 micron, this surface polishing cost, surface finishing cost also increases tremendously. So in AFM, extremely thin chips are produced. So this allows better surface finish, closure tolerances and generate more intricate surface features. So this is used for machining hard and difficult to machine materials. A need for automated finishing operations to substitute manual finishing operations are felt. So this AFM process can be automated. So we can automate this process, this abrasive flow finishing process. Okay. So AFM have the potential of better accuracy, higher efficiency, economy and consistency. So these are the requirements so that this abrasive flow machining process or abrasive flow finishing process have been evolved. So this AFM process, it is developed by Extrudon Corporation of USA. So after that many researchers have contributed in this process. In Japan also many work have been done, in US, Soviet Russia also many works have been done in Soviet Russia. And India also contributed many work on this abrasive flow finishing process. So this frame is a non-traditional finishing process that is used to obtain uniform radius generation. Suppose there is an intersection of two channels are there, intersection of two channels are there. So in that intersection you need a uniform radiusing, okay, for uniform flow of gas or liquid. So that's why AFM process is very much helpful. So any accessible, inaccessible areas, any complex geometrical shapes, irrespective of their internal geometry or external geometry, can be polished by this process. So edge of intersection deburring. So deburring, so is the very unwanted thing. So after drilling, this deburring is there. Okay, so these whatever deburring things are there, so that that kind of unwanted component can be removed by abrasive flow finishing process. So surface finish improvement of regular or irregular shaped passages can be done by this AFM process. Removal of recast layer. So it is also very important. After doing EDM operation, you see that in EDM operation, you know, there recast layers are generated. So these recast layers are nothing but whatever this molten material, it is redeposited on the already machined surface. So this recast layer, after deposition on the surface, already machined surface, it becomes very brittle and hard and porous. Okay, so this recast layer has to be removed before this recast layer has to be removed before this polishing, before these holes can be used for further work. Okay. So this recast layer can be removed by abrasive flow finishing process very successfully. So this process, AFM process, is also used to generate compressive residual stress. So compressive residual stresses, like in grinding operation, you can see that because of this heat generation there, okay, and this tool is actually every time it is in contact with the workpiece surface, this kind of compressive residual stress is generated. So that kind of compressive residual stress can be generated by using this abrasive flow machining process. So what is the working principle? Working principle of abrasive flow finishing process: material is removed from the workpiece surface by abrasive laden, pliable, semi-solid compound forced to flow to and fro across the surface to be machined. It is not a bulk material removal process, it is a selective material removal process, can remove sharp, regular, irregular peaks. So applications are, it is very much used in aerospace, dice industries, automobile industries. So it can be used for inaccessible and complex internal passages, small gears as small as 1.5 millimeter pitch circle diameter, orifices as small as 0.1 millimeter diameter can be easily polished by using this abrasive flow machining process. So hundreds holes or slots or edges can be deburred or reduced or polished by this process. Hydraulic and fuel systems in aircraft can be polished, and deburring of cooling holes in turbine blades. So these turbine blades, there is a deburred surface are generated after machining. So that deburring operation after machining can be done by this abrasive flow finishing process. So removal of EDM recast layer already we have discussed now. An intake port of automobile engines. Okay, so this intake port, if there are some burrs are there, if there are any irregularities are there, that can be polished by abrasive flow finishing process. So this is the working, this is a schematic diagram of abrasive flow finishing operation. Here you can see that this is one piston, this is another piston, two pistons are there. So this is the two piston, this is called top piston, this is the bottom piston, bottom media piston, and in between you can see this is the media. So this is the viscoelastic polymeric media. Okay, so this viscoelastic media, it is given to and fro motion. So because these pistons actually it is moving up and down, so these pistons, there is a simultaneous movement of these two pistons. So these two pistons actually move simultaneously. So when this top media cylinder, it is piston is coming in the downward direction, this bottom media cylinder also it is going in the downward direction. So that's why whatever this media is there, this media you will flow through the workpiece. So this is the workpiece here. So this media will flow through this workpiece, and it is means media is forcefully it is flown through the workpiece surface. Okay, so you have to design this zone, this workpiece surface, so that media will flow through the workpiece where you need a polishing. Okay, so because of this reciprocation motion of these pistons, this media will flow through the workpiece surface from top media cylinder to the bottom media cylinder, and while moving this one, whatever these abrasive particles are there in the viscoelastic media, it will remove the surface undulations from the workpiece surface. Okay. So this viscoelastic media is the main rheological media which is used in abrasive floor finishing process, which does the polishing. So we shall discuss further this working principle. Okay, so this is the schematic diagram of the process. Okay, so you can see here there is a hydraulic system. So this is the hydraulic system here. Okay, so from this hydraulic system you can generate up to 100 bar pressure. Okay, so there are two inlets in that hydraulic system. So this is one inlet and this is another inlet here. So this is one inlet, this is another inlet. Through this inlet it is moving. So there are two pistons, two types of piston. This is the hydraulic piston and this is the media piston. So this is the hydraulic cylinder and this is the media cylinder here. Two cylinders are there. Similarly, at the bottom also there are two cylinders are there. So this is the media piston and this is the hydraulic piston. So this media piston and hydraulic piston, they are connected by a connecting rod. So by this hydraulic unit you are giving this kind of reciprocating motion. Okay. So you are giving this one reciprocating motion, and this is the means workpiece fixture here. So while you are giving this kind of reciprocating motion, so media is flown through the passages here in the fixture where you need a finishing. Okay. So this media, viscoelastic media, it consists of abrasive particles. So why this viscoelastic media is flowing through the passages where you need the polishing, so the abrasive particles do the surface undulations by removing small chips from the workpiece surface, small chips from the workpiece surfaces. So this is the working principle of abrasive flow finishing process. So this is the hydraulic unit, is the 3-phase motor is there in that hydraulic unit, and there is a pump is there. So it can generate from 0 to 100 bar pressure. So this much pressure is required, okay, to flow the media through the passages where you need the polishing. So this viscoelastic media, actually it holds the abrasive particles. So this media has a elastic property. Okay, so this media has elastic property because when these abrasive particles will try to penetrate into the workpiece surface to remove the material. So this media, actually viscoelastic media, actually holds the abrasive particles. Otherwise what will happen? This abrasive particle will come inside the media with a certain means even with a small force. So this media has a viscoelastic property, that's why it does not go inside very easily. So it holds the abrasive particles. It gives the resistance to the abrasive particle to hold inside the media so that it can do the polishing operation. Okay. So this is the machining system. So this is the tooling medium. Here tool is there. So tooling medium, and this is the media here. So media is flowing from the top media cylinder to the bottom media cylinder and bottom media cylinder to the top media cylinder. So these two pistons, media pistons, actually this is reciprocating like this, and in between this abrasive this media, actually it is flowing from top media cylinder to the bottom media cylinder and then bottom media cylinder to the top media cylinder. While flowing, actually it will remove the surface undulations from the workpiece surface. Okay. So same, so this is the fixture zone where you can see that how this machining is going on. Okay. So as I told that the main rheological media is the this polymeric media. So this media, actually it does the machining operation by using these abrasive particles. It has certain property. It is a non-Newtonian fluid, obviously. Okay. So it is a non-Newtonian fluid. So media having high viscosity can held between the fingers like a rubber. You can see here between the fingers like a rubber, it can held like a rubber ball, which can be deformed by applying a little pressure. So it is a very soft media. So this media can be deformed by using a very small pressure. Also you can deform the shape. Means it can take the shape of the workpiece where shape of the surface of the workpiece from where it is moving. Okay. So, can be employed to machine tens of parts at the same time to enhance the productivity. It has a high flexibility, means it can be used to do a variety of jobs. Same media can be polished for a variety of jobs by changing the tooling operation. So, tooling operation means just you have to flow the media in such a way that in between this workpiece or tooling or inside the workpiece, you have to flow the media in such a way that only where you need the polishing. So, from there only this media will flow. So, you have to restrict the media where you need the polishing operation. Okay. So, can be used to do a variety of jobs by changing the toolings, machining parameters and media and abrasives. The semi-solid media, abrasive media is forced through the workpiece or through the restrictive passage formed by the workpiece and tooling together. More the restrictions offered by the passageway, larger is the force required. Okay. For if you give more restrictions, so you need a very large force, means very large, means you have to consider higher pressure from the hydraulic unit. Okay. So, abrasive particles act as a cutting tools here, hence it is a multi-point cutting operation. Okay. And giving very low material removal rate. So, it is not a bulk material removal process, it is a low material removal process. So, you can see here this kind of workpieces where small holes are there and media is flown through the at the internal surface, and while you are giving restriction to the flow of media, so media will flow through these holes also. So, while flowing this media through the holes, as it contains the abrasive particles, it will remove the surface undulations from the workpiece surface, and whatever undulations are there into that hole, so it will be removed. So, it will be a uniform hole. Okay. So, deburring finishing of inaccessible areas you can see here can be done by using this abrasive flow machining process. So, this is the media here you can see, it can be kept inside your in your hand. So, it will take the shape of the workpiece surface. So, here it can take the shape of your hand fingers. Okay. So, it can take the shape of the workpiece surface. So, it is a pliable. Okay. So, it is a flexible pliable media. Okay. It can take the shape of the workpiece surface to be polished. So, these are the different abrasive flow machining conditions, it is shown here. So, you can see here this media actually flowing through the holes perpendicular to the cylinder, it is coming here in the first case. And here we can see there are two platforms are used. One platform is for polishing, another platform actually for removing the whatever media is there from the polished surface. So, here they have used two platforms. This is another schematic diagram of the abrasive flow media. So, in this setup you can see the machine, tooling and media here. Okay. So, media pressure here they have considered 0.7 to 0.22 megapascal here. So, to maintain the constant media viscosity, coolers are used for lowering the temperature. So, this media property actually dependent on the temperature of the media. So, this rheological property of this media depends on the temperature. Okay. So, with the increase in the temperature, this property actually viscosity actually reduces. So, we need the machining operation to be done at a constant viscosity. Okay. So, that is why during machining, during polishing itself, we have to maintain the temperature of the media, so that its viscosity remains constant. So, that is why from some external means you can use some coolant. Okay. So, you can use some coolant to flow outside this media, so that this temperature of the media can be maintained. Okay. This temperature of the media can be maintained during machining operation. Okay. So, tooling, this tooling is used, what I told that it is used to confine and direct the flow of media to the appropriate areas, to selectively permit or block the flow. So, you have to selectively permit to flow, or you can block the flow. Like you can see here, so this media is flowing here. So, this portion you want to polish and this portion you want to do the radiusing operation. So, for doing this radiusing operation, you have to flow this media like this, you have to take a right turn, here also you have to take a left turn. So, that is why this is the block is kept just exit of this hole, so that this media can flow right hand or left hand side. Okay. So, here it can remove, it can do the radiusing operation there at the corner of this block. Okay. So, this is one of the operation here. that can be done by using this FM operation. So, this is the radiation operation. Okay, so that's how it is told, to selectively permit or block the flow of media into or out of the workpiece passages while debarring, radiusing or surface improvements are desired. Tooling for AFM media machine is designed with two ends. So, tooling for AFM machine is designed with the two ends to hold the parts in position. Okay. So, here to hold the parts in position and to contain the media and direct its flow. So, tooling is done to contain the media and to direct its flow. So, here it is one of the tooling here. So, this it is used to flow the media to direct this flow. Okay. So, passages of similar nature processed in parallel, like here this passage and these three workpieces, these passages are same. So, it can be polished together. Okay. So that's why passages of similar nature can be polished parallel for non-uniform cross section MRR of the net. So here you can see here cross section is more, here cross section is less. Okay. So here you can expect that non-uniform polishing will be there where cross section is less, and where lesser restriction is there, restriction of the flow is there. So you will get the lesser material removal rate. So material removal rate at the narrowest section will be maximum, and for the widest section it will be minimum. So you can use the replaceable inserts, like here you can use replaceable inserts are used here. Okay, so replaceable inserts can be used to restrict the flow of the material. So these inserts may be nylon, Teflon or hardened steel for restricting the flow of this media. So lives of these inserts can be increased by thousands of parts with proper design. Okay. So now we can see here these restrictions. So here this small cross section, here it is the bigger cross section. Okay. So we can expect that means higher material removal rate will be here than this material removal rate here. Okay. So here also lesser restriction, here means maximum restrictions are here, here lesser restrictions are there. So this kind of gears tooth can be polished by this abrasive flow machining process. Okay. So here outside you have used a cylindrical fixture, okay, to restrict the flow of the media just outside this cylinder, to restrict the flow of this media just outside this gear. So if you reduce the diameter of this cylinder outside this gear, okay, so in that case it will be more restricted, this flow will be more restricted here. Okay. So if we increase the diameter of this cylinder, so more lesser restrictions will be there. Okay. So these gears at the same means outside, at the outside you can use this kind of nylon tooling, okay, to restrict the media. So any kind of complex surfaces can be polished by using this process, abrasive flow machining process. So another thing is that media. So another component of this abrasive flow machining process is the media. So this media is a pliable, easily molded, it can be molded easily, it can take the shape of the workpiece surface, resilient enough to act as a self-deforming grinding stone. So grinding stone, you see, you know this grinding stone is used in grinding operation. This grinding wheel is called the grinding stone. What this grinding wheel, this whatever stone is used in grinding wheel, it cannot take the shape of the workpiece surface, but here it is also similar to the grinding stone here, but it is self-deformable according to the workpiece surface. Okay, so that's why it is called self-deformable grinding stone. Same grinding stone polishing media can be, it is used, similar features, but it can take the shape of the workpiece surface to be polished. So that's why it is called self-deforming grinding stone. So it consists of a base material, this media consists of a base media. So this base media is the viscoelastic or viscoplastic media made up of organic polymer and hydrocarbon gel. Okay, so now with this base media you have to add these abrasive particles. Okay, so you have a base media, viscoplastic or viscoelastic base media is there, that is hydrocarbon gel and organic polymer is there, and with this you have to add within this base media you have to add the abrasive particles to make the media here. So these abrasive particles has to be homogeneously mixed with the media. So stiffest media is used for largest hole. So suppose you want to make the long holes you have to make, you have to polish. Okay, so in that case you have to use the stiffest media. because stiffest media in that case you can see in this figure, if you use the stiffest media, so everywhere at every cross section this media velocity will be uniform media velocity will be there. So you need a uniform polishing along the length of the hole, you need a uniform polishing. So stiffest media is used for longer hole, okay, and soft media is used for smaller diameter hole. Because smaller diameter hole you have to flow the media, so you have to use the soft media. Also in that case, in soft, here you can see at the center velocity is high, okay, high velocity at the center, and at the surface there are low velocity. But for stiffest media, everywhere this velocity profile is constant. So for making small holes, for polishing small holes, means less stiff media is used. So this less stiff media, so it has a center velocity is high, at the surface its velocity is less. So this media can flow anywhere, so it can be used for radiusing also. So it can results in a greater radius at a passage opening. Okay, so whatever if this passage opening is there, if you generate a greater radius, you have to do the radiusing operation, you have to use the soft media. So you can see here this kind of surface can be polished by this FM media. Any kind of surface, it will take the shape of the surface to be polished. Okay. So high stiffness of the media results in a kind of pure extrusion, while soft media lead to a faster flow at the center than along the walls. Okay. Stiff media finishes the passageway more uniformly, while the less stiff media results in a greater radius at the passageway. So now after for making the new media, you have to mix this viscoelastic polymeric media with the abrasive particles, and you have to move this media over in scrap workpieces for 20 to 30 times, so that homogeneous mixture of abrasive particles with the base media can be made. Okay, so these abrasive particles are different types of abrasive particles are used, like aluminum oxide, silicon carbide, then boron carbide and diamond, okay, with 8 to 700 mesh size are used. When media is machined an amount of 10% of its weight, suppose you are doing the machining and your initially your media weight of this media is suppose 1 kg. Now after machining, whatever debris particles are there, that will also come into the media. Okay. So after machining for many components, you will see this media weight will increase, because whatever debris particles they are also mixing with the media. After some time, if it happens that this weight of the media has now increased to 1.1 kg now. So it is 10% increase in the weight of this media. Okay. So now this media can be discarded. When this media machined by amount 10% of its weight, okay, so then in that case it can be discarded. So another media is aluminum oxide. So this aluminum oxide is inexpensive, general purpose abrasive particles it is. Okay, silicon carbide, it has a high stock removal rate, degradable and economical. Boron carbide relatively expensive and well suited for abrading hard materials. And diamond abrasives are used to process most difficult materials like tungsten carbide, thermal recast layer. Because this thermal recast layer and tungsten carbide, these are very hard materials. These hard materials can be machined by these diamond abrasive particles. So larger grid size enable quicker cutting without degrading the surface finish, and final grid size 600 to 700 mesh are added to existing media to increase the media stiffness less expensively than by adding a stiff media. Okay, so stiffest media can be machined with the same basic. So means for making the stiffest media, what is the concept is that you have to use the base media of the or viscoelastic media should be stiffer. But if you have a same media there, okay, so in that case what you can do, you can add more concentration of these abrasive particles. In that case it can be considered as a stiffer media. So this extrusion, they have started this machining process, abrasive finishing process. It is extensively used in industry for polishing complex surfaces, complex geometries, Okay, irrespective of their magnetic or non-magnetic property of the workpieces, any kind of workpieces they are polishing. Okay, so this media actually very costly because it is patented and it cost around 5 lakhs per kg. So it is a very costly media, but you can use in your own media. So many researchers they developed then alternative solution for this FM media. Okay, so you can use that kind of media and it can give almost similar efficiency. Okay, so these are the different process parameters of the abrasive flow machining process. So what are the output parameters? Output parameters obviously that is material removal rate, how much material removal you are getting, and also surface integrity. So this surface integrity, it consists of surface accuracy, tolerances, and then surface roughness, subsurface damage. All these things actually comes into the surface integrity. So these are the output parameters. What are the different input parameters? Input parameters you can see workpiece hardness. So hardness and composition of this workpiece material. Okay. Now machine and tooling, what kind of machining you are doing and what kind of tooling you are doing, you are making, and then fixture design, cylinder size, clamping pressure, all these are actually workpiece material, input parameters for workpiece material. Then adjustable parameters, you can control the pressure, so you can increase or decrease the pressure, and you can control the finishing cycles or finishing stroke. So one cycle means top media cylinder to the bottom media cylinder, and then from bottom media cylinder it will come to the top media cylinder, then it will consist of a one cycle. One stroke means from top media cylinder to the bottom media cylinder, it will consist of one stroke. Okay. So two strokes consist of one cycle. Now component geometry, that passage shape, L by D ratio, length by length to diameter ratio, and length of flow path, all these are actually component geometry. And media, what are the different parameters of this media? Medium viscosity. You can use low viscous media, medium viscous media. Okay. So different kinds of media or high viscous media also you can use. Different kinds of media based on your requirement, you can use different kinds of media. Volume flow rate of this media also one of the another parameters. Then abrasive type is another parameter, and abrasive concentrations also another parameter. So generally 60 to 66% concentration of abrasive particles are used in case of abrasive flow machining process. So these are the again different process parameters. Now you can see workpiece parameters are initial surface roughness of this workpiece, it also matters. So if it is very highly rough surface, okay, so then you will not get that much efficiency because it is not a bulk material removal process, it is a polishing process, and also small chips are generated. Okay. So initial surface roughness of the workpiece also matters. Passage geometry also matters, how this passage we have generated by using the tool. Passage area, passage length, material type, hardness, all these are the workpiece parameters. Media characteristics like medium viscosity. So viscosity of this polishing media is the main thing. Okay. So by changing this media, you can use means for different hardness of this workpiece material, you have to change the rheological properties of this media. Okay. So you have to change the rheological properties of this media by changing the viscosity of this media. Okay. Means by changing the rheological properties of this media, okay, or that is by changing the viscosity of this media, you can polish different hardness of the workpiece, different workpiece with different hardness. Okay. So media characteristics, media viscosity, percentage of abrasive concentration, media modulus of elasticity, media density, abrasive grain size, abrasive type, abrasive hardness and shape. Machining parameters are main parameters of extrusion pressure and finishing cycles, media flow rate, percentage reduction in surface roughness, cutting force, normal and tangential cutting forces, media entry profile to workpiece. These are the different machining parameters are there. Okay. So William and Rajkar in USA, they did extensive research on this abrasive flow machining process. There they have used three kinds of media. Okay. So at the middle you can see that they have used three kinds of media. One is the low viscous media, second one is the medium viscous media, and third one is the medium high viscous media. So, first one is the low viscous, medium viscous and medium high viscous media. Three types of media they have used, and they have measured the mean material removal rate. Okay. So, what are the material removal rate there? So, this material removal rate, it is a linear material removal rate they have considered. Okay. Linear material removal rate, it is not a volumetric material removal rate. This linear material removal rate is here inch per second. Okay. Inch per second they have considered as the output parameter, and they have seen that there is a significant difference between linear low viscous media and medium viscous media, and low viscous media and high viscous media. So, you can see low viscous media there is a very less material removal rate, but medium viscous media you can see when you are increasing the viscosity of this media, your material removal rate increases, and when you are going for medium high viscous media, still it is increasing. So, you can conclude that with the increase in the viscosity of this media, your material removal rate also increases, material removal rate increases. Okay. So, there is a significant difference between low viscous media and medium viscous media and low viscous media and medium high viscous media. Okay. And there is hardly any improvement in medium viscous media and high viscous media. Okay. So, all these experiments are conducted at 1500 psi pressure. Okay. So, and these 10 cycles they have considered for these experiments, and abrasive concentration is 66% they have considered. And you can see they did experiments at different pressure, 500 psi pascals per square inch, 1000 psi and 1500 psi they have considered. Three pressures they have considered, and you can see with the increase in pressure from 500 psi to 1000 psi, you can see there is a significant increase in the material removal rate. But when you are going for 1000 to 1500 psi pascals per square inch pressure, psi pressure, so there is hardly any improvement from 1000 psi to 1500 psi. So you can say that here this maximum or optimum pressure here is 1000 psi, because beyond 1000 psi you are not getting any improvement into the material removal rate. And here also they considered three different kinds of material, okay, AISI, CRS and aluminum. So, here from harder to softer material they have considered. So, aluminum, as it is a very soft material, you can see its material removal rate is very high, but for the AISI and CRS, these two kinds of material, you can see their material removal rate is not that much high. Okay. So, now they have considered final surface finish. So, means final surface finish, how much improvement in surface finish they have achieved. So, you can see with low viscous media, you can see there is surface roughness, final surface roughness is not that much good, but with the increase in the medium viscosity, you can see from medium viscosity to the high medium viscosity, you can see final surface roughness of the work is actually decreases. Okay. So, this final surface roughness of the work is decreases. So, this medium viscosity has a role on the surface finish as well as material removal rate. Okay. So, now if you want to do the machine polishing on a harder material, obviously we shall go for harder, means we shall go for this higher viscosity of this media, and when we are polishing the softer material like brass and aluminum, then we shall go for lower viscosity of this media. And also you can see here with the 500 psi pressure, with the 500 psi pascals per square inch pressure, you can see here your final surface roughness is not that much good, but at 1000 and 1500 pressure, you can see your final surface roughness improves. Okay, your final surface roughness improves with 1000 and 1500 pressure. So, also there is very hardly any improvement within this 1000 and 1500 psi pressure, there is hardly any improvement. And also effect of flow rate on metal removal is insignificant. So now this active grain density is a very important parameter in case of abrasive flow finishing process. So active grain density you have to check to see how many abrasive particles are there in a square millimeter area. Okay. So this active grain density counted over the surface of the media by viewing through the optical microscope. You consider a 1 by 1 millimeter square area. Okay. So these abrasive particles, active grains means these abrasive particles actually at the surface of this media, it only takes part during the polishing process. So you have to count this one for numerical simulation. Okay. And you will get the idea from experience also how many active grains are there. Based on that, your polishing performance of the process will be improved. So if active grain density is less, you have to increase the concentration of these abrasive particles so that this active grain density can be increased. So it can increase, this active grain density can be increased with the increase in the percentage concentration of abrasive particles. Also increasing the extrusion pressure also, your active grain density can be increased. Okay, so here you can see this is the media here. Okay, so this media you can see under microscope. So these are the white spots. These white spots actually these are the abrasive particles. Okay, it is shown under 50x optical microscope. Okay, so now come to this application parts. You can see these kind of turbine blades can be polished, because after machining these turbine blades you will see different kinds of bars are there, and also machine because of machine by these different kinds of machining processes are used. So you can see bars are there, also you can see the non-uniform polishing. So after doing this, after machining by other process, you can do the polishing operation by abrasive flow finishing process. These kind of complex shapes can be polished by AFM process. Okay. So extrusion die, you can see here extrusion die, these dies can be polished by AFM process. And in turbine blades there are cooling channels are there. So these cooling channels are non-uniform cross sections, these kind of cooling channels are there. So these cooling channels also can be polished by abrasive flow finishing process. So what are the different forces are there in abrasive flow finishing process? So you can see that this media is flowing through this cylinder. Okay. So these are the abrasive particles are there. These abrasive particles, it is indented into the workpiece surface, and this indented workpiece it is moving towards the because of this axial force, these indented abrasive particles are doing surface indolutions from the workpiece surface. Okay. So there are two forces are there. One is the radial force. This is the radial force Fr. Okay. F small r radial force, and this is the axial force. This is the reciprocating motion. This is the axial force F is there. Okay. And also there is a resistance force F capital R, capital F suffix capital R. Okay. This resistance force is there. So it is based on the hardness of the workpiece material. Okay. So when these abrasive particles are indented because of this indentation force, this axial force actually it will try to remove the surface undulations. Okay. So this force ratio of Fr by Fa increases by increasing the extrusion pressure, abrasive concentration, and it decreases in grain mesh number. Okay. So it is proposed by Godana et al. In 2004. And there are three different conditions are there. When axial force is greater than, this axial force is greater than this resistance offered by the process, by the media, resistance offered by the workpiece, okay, then there is a chip formation or flowing operation is going on. And when this axial force is just equal to the resistance offered by the material, in that case just finishing is on the at the edge of to start. And when this axial force is less than your resistance offered by the workpiece material, grain will rotate inside the medium. Okay. So there will not be any polishing in that case. So classification of AFM process, there are three different classifications are there. One-way AFM process, two-way AFM process, and orbital AFM process. So this is one-way AFM, we shall discuss later in the next slide. Okay, it is partially through cavity. 2FM it is through cavity, and orbital AFM it is used for blind cavity. So types of AFM you can see here. This is the zone of the workpiece here. So here small holes are there. Okay. So you cannot do the reciprocating motion here. So this media is flown through this media cylinder. Now it is flowing through this kind of fixturing arrangement. Now this media is going outside here. So this is the one-way AFM process. Like this kind of holes, small holes on the cylindrical surface, So you can polish by this one FM process. This top surface actually it is blocked. So one entry, one exit is there for the media to flow through these small holes. So this kind of holes can be polished by one-way FM process. So this is the two-way FM process, that is a through hole is there in this workpiece. By two-way FM process it can be polished, and this is the orbital polishing process. Here you can see this is the workpiece surface, top of the workpiece surface, that is a complex shape is there. So this complex shape can be polished by this kind of orbital polishing process. So here this is the media cylinder, media piston, another media piston is here. So it will move here. So this kind of reciprocating, this kind of motions are given. So these kind of motions are given. So that this media can polish the top surface of this workpiece. So this is called orbital polishing process. And here at the top surface actually one tool actually it is rotated. This tool surface is actually it is the shape of the workpiece surface, similar to the shape of the workpiece surface, so that uniform pressure can be generated on the media. Okay. So how to enhance the performance of this abrasive flow finishing process? To enhance, there are different researchers actually they develop different process to enhance the performance of this abrasive flow finishing process. So this is actually centrifugal assisted abrasive flow finishing process here. Okay. So here you can see in this is the workpiece here, at this workpiece at the center actually there is a centrifugal rod. So here you can see cross section of this workpiece here. So this kind of triangular rod, this is the rhombus rod, this kind of square rod, this kind of rectangular rod actually they kept there. This is the cross section of this rod, and these rods actually it rotates with a certain RPM. So this CFD centrifugal force rods actually rotates with a certain RPM, and media at the same time this kind of reciprocating motions are given. So because of this actually centrifugal force of this rod, what happens? This tangential force are generated. This tangential force actually acts to remove the surface and to enhance the surface to remove the surface undulations from the workpiece surface. Okay, so you can see this tangential force is generated which helps in removing surface undulations. This is the one kind of spiral polishing process here. You can see this is the workpiece here, and one spiral tool is actually used like our drilling tool, where these spiral grooves are there. So first this bottom cylinder actually it is filled up with the media. When you are rotating, this media will flow through these spiral grooves in between this workpiece fixture and the tool. So this is the workpiece here, in between the gap it will flow and it will come to the top media, then again you can move to the bottom media by rotating in reverse direction. So in that way internal surface of the workpiece can be polished. Okay, so this is the actual excited view. Here in this zone, when media is flowing here, so flowing here at the internal surface of this workpiece can be polished. Okay, so this is you can see here. Another thing is that actually you can rotate the media here by an external means. So this is called rotational abrasive flow finishing process. You can rotate this media itself. So here whatever workpiece fixture or workpiece tool is there, that can be rotated by an external means. Okay, you can see what are the forces are there. This radial force is there because you are flowing, you are giving reciprocal motion. Radial force is there, and this axial force is there, and this tangential force or correlative force is added here. This correlative force actually it is generated because of this rotation of this media. Okay, so this tangential force will help in cutting the surface undulations. So now we can see in normal AFM process, this media will flow in the linear direction, but here in this case of rotational AFM process, this media flows in a spiral path. This kind of spiral, it flows in a spiral path. Okay, so as it is flowing through a spiral path, okay, so it will generate cross-hatch pattern into the workpiece surface. So these cross-hatch patterns are generated on the workpiece surface. So this is actually helpful to retain the oil during during your actual polishing of this cylinders of the cylinders of the engine, okay, engine cylinder, and also it is taking more path. So it is traversing more path. Okay, so that's why more area are actually covered. So it is not covered because these abrasive particles are covering in a straight line path. So it is not covered more area, but in this case in RAFM process it is covering more path. Okay, so now you can see total cutting force is the axial force and resultant of this axial force and tangential force, and it is the alpha is the helix angle here. So it can move away. So based on your actually rotational speed and also axial motion of this media, so this helical path can be varied. Okay, so this kind of process patterns you can see here. This kind of process patterns are generated on the workpiece surface. So FM picture also you can see before polishing actually this kind of surface undulations, which is grinded surface undulations are there. After FM process, whatever these surface undulations are there, actually it is totally removed. So FM by MMC means metal matrix composites also can be polished by abrasive flow finishing process. Okay, so forces also you can measure. What are the forces are there? So you can use the strain gauges. So this plate actually attached in the fixture. Okay, at the top surface actually you can use 8 strain gauges at the top and bottom surface. You can use the 8 strain gauges. So by the deflection of the strain gauges, you can measure the how much force in the how much this axial force is there. And also at the surface also we can put the strain gauges. Okay, like in drilling operation. Okay, so by this movement of by tension and compression of these strain gauges, okay, you can calculate the what are the radial forces are there. So it can be measured experimentally, these forces, radial force and axial forces. So you can see here one applications, this at the surface of this cylinder you can see so many holes are there, that holes can be polished by this AFM media. Okay, so same thing here, so many holes, thousands of holes can be polished, external holes can be polished by this AFM media. So this kind of turbine blades can be polished by this AFM media, this kind of small holes can be polished by this, finishing holes can be polished by AFM media. So I told initially that this kind of intersections of these holes here, so many holes are actually, pipes are actually connected here. Here you can see it is not a smooth at the intersection of these two holes. This intersection of these two holes can be polished by the abrasive flow finishing process. These kind of small components can be polished by AFM process. So these medical parts also should be bars free, it should be highly polished, these medical parts. So these hard valves actually it is polished by abrasive flow finishing process. Okay. So like this so many applications are there for this abrasive flow finishing process. So what is the process performance? As much as actually nanometer level surface finish can be achieved, we can see 50 nanometer up to 50 nanometer surface roughness can be achieved. Surface irregularities like deep scratches, large bumps, outer roundness cannot be, and taper cannot be polished by this process, because here polishing is done by uniformly every year. So that's why outer roundness, all these things can be corrected properly by this AFM process. Maximum limit or diameter of the hole that can be polished, minimum diameter of the hole that can polish is 0.2 millimeter, and largest diameter is 1000 millimeter. Can produce dimensional tolerance plus minus 5 micron. A perfect edge can be reduced to anything from 0.025 to 1.5 millimeter. So applications used for finishing extrusion dies, nozzle of flame cutting torch, aerofoil surfaces of impeller, fuel spray nozzles, fuel control bodies, bearing components, deburring of aircraft valve bodies, spools, removing of recast layer after EDM, LBM, employed for finishing and in aerospace, automobile, semiconductor, medical components. Resistance offered to flow the air by blades, nozzles, diffusers, etc. can be adjusted or tuned accurately by modifying surface using AFM process. AFM improves mechanical fatigue strength of blades, discs, hubs and shafts, employed for removing coke and carbon deposition and to improve the surface integrity, employed for removing left out light machining marks, and for radiusing and deburring of the cooling turbine blades are done by one pass of abrasive flow machining process. Okay. So dies, and it is mostly used in dies and mold industries. Multiple passages can be processed at one time. Surface finish can be improved to a large extent with least change in dimension, saves considerable time compared with the finishing with skilled hands. Finishing of 2-stroke cylinders and 4-stroke engine heads is done using AFM for improving airflow and better performance. Stainless steel impeller made by investment casting is polished by up to 0.37 micron. Uniform finishing of threaded holes are there. Disadvantage, fixtures can be expensive and high capital investment is there. Okay. So, thank you.